Okay, so for part 2 of homework 8-2 here, we're picking up question 9, and this is a good question. This is kind of the end of section 8-2 notes, where we saw we had physical pendulums, right? So they're asking us what's the frequency of the oscillations. I cannot just use the period for a pendulum to be 2 pi square root of L over G. I cannot do that because it is a uniform meter stick that has a certain amount of mass, right? So if it's a physical pendulum, again, that equation and the frequency equation go out the window. So instead what we can do, we saw that the frequency for a physical pendulum was 1 over 2 pi times the square root of, instead of G over L, it's mg times the length divided by I, right? So this is my equation for the frequency of a pendulum, if that pendulum has mass at least, right? So anyway, so I've got this. So really then the big question of this becomes, obviously they don't give me the mass of the pendulum, and that looks at first like it's going to be an issue. But ultimately the biggest question becomes, what about the moment of inertia? And so this actually ties nicely back into the last chapter that we just looked at, right? Finding the moment of inertia for this meter stick that's being pivoted at that point. So I'm going to kind of just sketch a basic example here. So again, this meter stick is being pivoted at the 20 centimeter mark. It does tell us it's uniform, which means we know its center of mass would be right there in the middle, right? So we know that the length between the two would be 0.3 meters. So that's going to act as my L. That is the length of the lever arm, if you will, right? So I've got that without too much trouble. I've got my L. So then the question is, how do I find I? Well, again, this actually goes back to the parallel axis theorem. To find the moment of inertia of an object pivoted not about its center of mass or the end, right, I'm going to use the parallel axis theorem to help me out with this. So the parallel axis theorem says the moment of inertia equals the moment of inertia of the center of mass plus m times d squared, right? And that d conveniently looks a lot like L because it actually is going to be, right, L is going to represent the distance between the pivot point and the center of mass. So that actually is going to be that same 0.3 again as I solve this problem. So anyway, the moment of inertia, right, which is what I'm looking to solve for, equals the moment of inertia of the center of mass. So if I were to pivot that meter stick, if I were to pivot that rod in the middle, the equation for the moment of inertia of that is 1/12 m times the total length of the rod. So I'll go ahead and just plug in the full 1 meter squared, plus m times, again, that length to the pivot point. How far away is the pivot point? Which is 0.3 squared, right? So obviously you could try and get a common denominator here. I'm going to go ahead and just get this as a decimal. My moment of inertia ends up being 0.173 repeating times the mass of the rod. And notice the mass of the rod, once again, I don't know, so I just leave that in there. But this is where it actually works out very nicely for us, right? So now that I know the moment of inertia, and I know that this is the frequency equation for a physical pendulum, then bringing that all together, I got the frequency equals 1 over 2 pi times the square root of m times 9.8, my acceleration of gravity, times L, which is 0.3, divided by the moment of inertia of this pendulum, which again is 0.173 repeating times m. And notice we don't need the mass of the rod because the mass is in both the numerator and the denominator, so it cancels out, and everything else is a known value, right? Everything else is a known value. So solving for this frequency, I end up getting about 0.66. So about 0.66 from calculating, and that is our answer here, right? The frequency of the oscillations, it takes about 0.66 cycles per second. So it takes about 1.5 seconds for a cycle to happen. But anyway, a good question to make sure you're comfortable solving, a very nice one for tying both this chapter and the new material for the physical pendulum with the previous chapter and finding the moments of inertia for various objects. So again, nothing too crazy here, but a good one to make sure you're comfortable kind of approaching and solving. Question 10 then is very similar to question 9. So question 10 says a large stick pivoted about one end, so they do tell us it's about one end, allowed to swing back and forth with no friction as a physical pendulum. And again, that is a key term that tells me. So ultimately they're asking us for what is the period, or if the period, right? But I cannot just use this equation. I cannot just equal the period to 2 pi times the mass over, pendulum, so the length over gravity. I cannot do that because the pendulum has significant mass. It is a physical pendulum, and therefore this equation goes out the window. However, much like for question 9, and I'm going to invert that equation I used for question 9, right? The period for a physical pendulum is 2 pi times, then again I'm inverting the previous function. So instead of being mgl over I, it's actually going to end up being I over mgl, right? So inverting that function to solve. So again, I end up with I over mgl here, and I think I said that right, but I may have said that backwards. But anyway, so the period equals 2 pi and then the square root of I over mgl. And in this case, I look for what information I do and don't know. And the only measurement that I don't know, since they do give me the mass of the pendulum, is the moment of inertia. So I don't have to worry about calculating that. I can actually just find the entire moment collectively by using this equation. So I've got the period, I've got the mass, I've got gravity, and I've got the length. And I'm just going to substitute all of that in. Right? So the period of 6.90 seconds equals 2 pi times the square root of, again, the moment of inertia, which I don't know, but I know everything else. 5.4 for the mass, 9.8 times for the acceleration times gravity, and then the length of the pivot would be how far from the pivot is it, so 1.80 meters from the pivot. So solving this again for the moment of inertia, just a little bit of algebra, and we should end up getting about 114.88. So about 114.88 kilograms times meters squared. So there's my moment of inertia for this rod. Okay, so that finally brings us to question 11, which at first looks very intimidating because they do have parts A through H. However, each of these parts is actually pretty easy to identify, except maybe part E. So obviously I'll work through this whole thing, but again, bear with me because I think most of this you guys are going to be pretty comfortable with. So for example, finding the amplitude. Well, the amplitude is just whatever number is in front, right, of our cosine function. So in this case, the amplitude would be 2.0 meters. Right? There's nothing to calculate, nothing to compute there. It's just identifying that piece of the puzzle. Right? So I've got my amplitude without too much trouble. Same type of thing for the period. So the period, right, we know comes from the inside of the function. So ignoring the phase shift, the phase constant, we're just going to look at this part of the function. Well, 10t could represent any number of things. We know 10t would be omega times t, or it could be 2 pi f times t, or it could be 2 pi over the period times t. And in fact, I'm going to choose that last one, right, to represent the 10t. So all I'm going to do to solve part B is 10t equals 2 pi over the period times t. Obviously, I have a t on both sides, so that t cancels out. So 10 equals 2 pi over the period, which means the period equals 2 pi divided by 10, which obviously works out to be about 1/10, exactly 1/10 of 2 pi, so about 0.628 seconds. Okay, so again, parts A and B, hopefully nothing too crazy with either of those parts. It's just breaking up the information as I see it. Part C, as soon as I know the period, part C becomes pretty easy, right? Because now I can use my period, which I know is 0.628, and my period equation, which is 2 pi times the mass divided by the spring constant. So now that I know this is 0.628 seconds equals 2 pi times the mass, which is 0.05, divided by the spring constant, which is my only variable. Solving this out, now this actually again works out pretty conveniently. 0.628 divided by 2 pi ends up being about 0.1. So I end up with this on both sides. I square both sides and solve for k, and ultimately I get k to be about 5 newtons per meter. Okay, so just a little bit more algebra, but hopefully the setup there is easy enough. And then finally, part D is pretty easy in terms of the easy portions here. Part D is pretty easy because all I have to do for part D is I have to know what the phase constant is. As soon as I realize that the phase constant is whatever shift I've done on this function, I don't even have to calculate anything. I just need to know that my phase constant is negative pi over 4. Right? That tells me where I'm starting at. That tells me what the function is doing to start off. So then E, this is where it starts to get a little bit trickier, but again, if you take your time, it's actually not that bad. So for part E asks us to find the initial conditions, and what I want from that is I want to find what is its starting position and which way is it moving. So is it moving left, right? Is it going in the positive direction or the negative direction? Okay, so that's what I mean by the initial conditions. So if I think about this, well again, I just identified that the phase shift is negative pi over 4. So think about that in terms of the unit circle, right? So here's my unit circle. If I'm thinking in regards to that, negative pi over 4 is negative 45 degrees, right? So negative pi over 4, negative 45 degrees. So that would be at this position down here, right? So if I want to find the initial starting position, I just want to find out what the horizontal component of that is. Well, think about, I'm going to blow that triangle up a little bit bigger, right? It's a 45, 45, 90 triangle. So I know that this angle here would be 45 degrees, right, as would this one. I know the hypotenuse of that triangle. I know the hypotenuse of this triangle would be the altitude of the entire motion, right? So it's 2.0 meters as the altitude of the motion. So I have 45 degrees, I've got the altitude. If I can find this component, I can find that position, right? Because that's where its horizontal location would be at that instant in time. So all I have to do is set up a little bit of trig, right? The cosine of 45 degrees, or the cosine of pi over 4 if I'm using radians, would equal my variable that I'm looking for, my initial position, divided by 2. So solving for that initial position, I do get a positive 1.41, and that tells me this is where the object starts at, right? It starts at 1.41 meters in the positive direction. The other aspect that I do want to make sure you're comfortable thinking about right now, which direction is it moving? Well, since the phase shift was a negative pi over 4, it's down at this location, so as we're going around the unit circle, wouldn't the horizontal component be going to the right at that location? So this is moving in the positive direction. Okay, so it's at that position and moving in positive direction, right? So that is the initial conditions. Those are the initial conditions I want you to identify. If you also wanted to find the initial velocity and the initial acceleration, you definitely could, right? You would just have to set up a velocity and acceleration function and then plug in the time for that to happen. Again, I won't make us do that for this part, but if you wanted to practice that, that would certainly be something you could do, right? So then for part F, find the maximum velocity. Well, finding the maximum velocity, we've seen it before. The easiest way to do that is 2 pi times the amplitude divided by the period. Since we've identified the amplitude to be 2, and we identified the period to be 0.628 seconds, there's really nothing to this. It's just a simple matter of calculating, right? Ends up being about 20 meters per second. So that's my maximum velocity. And again, that could help me if I wanted to find the velocity for the initial conditions. I could then set up my velocity as a function of the maximum velocity in time, right? I could set up this as a function of time and go from there, but I won't make us worry about that for right now. Part G, right? Part G asks us to find the maximum or the total energy, right? And to do that, you can do any number of things. You can do either the maximum potential energy, which we know would be 1/2 k times x squared. Since we don't know the spring constant, though, that's not going to be the easiest route. So instead, I'm going to find the maximum kinetic energy, which I know is 1/2 mass times that maximum velocity, which I just found, right? So 1/2 the mass, which they told me again was 0.05, and then times the velocity, which I just calculated to be 20 meters per second. So 1/2 times that squared. So anyway, doing that, we end up getting 10 joules. Works out very nicely. The maximum, the total energy for the system is 10 joules of energy. Right, so almost done then, finding part H. Part H does ask us to find the velocity at a certain time, but the good news is since they give us the time, we can just set up my velocity function like I was starting to do before. So velocity equals negative velocity max times the sine of the inside function, and again the inside we already know is 10t minus pi over 4, so I don't have to do anything crazy there. So all I have to do is plug in my maximum velocity, which I just found out was 20, so negative 20 times sine of, and then plug in the time that they're specifying, which they say is 0.4 seconds, so times 0.4 minus pi over 4, and so then solving for my velocity, I should get that to be about 1.46 meters per second. Right, so about 1.46 meters per second. And again, hopefully this question wasn't too bad. Definitely a lot of information going on. Probably part E was tricky to get set up, and maybe the last couple parts here as well. But my hope is that the first few parts of this were actually pretty easy. So while it is a lot to identify, nothing too insanely difficult, I hope. But anyway, that finishes out homework 2 here. So if you do have any questions over the first 2 homeworks, feel free to let me know.